People are fascinated by light. I mean, just glancing over at a display of flashing lights can grab my attention. Do you ever remember sitting around a campfire, staring at the flames, and just being totally transfixed? Almost like if you're watching TV. It's comforting, and it can even be hypnotic. Recently, technology has made creating light a whole lot easier to do. For that, we have this little guy to thank. The light emitting diode, or LED for short. LEDs have a lot of different uses, from a simple power-on indicator to traffic signals. LEDs use about 10% of the energy of a traditional light bulb, and they can last about 30 times longer. That makes them a pretty big hit with businesses looking to do large-scale visual communication. The first person to ever report the effects of a light-emitting diode was researching another form of communication. In 1907, a man by the name of H.J. Round was researching radio waves for Marconi Labs. He was using a device called a cat's whisker detector, which, no, does not contain any cats or part of cats. Round was searching for a sweet spot on a crystal of silicon carbide when he noticed something odd. Part of the crystal started to glow. It lit up a pale yellow. And that was an LED. H.J. Round's crystal experiment was so cool and simple that I had to try it myself. So I got a piece of silicon carbide, then I hooked that up to the positive lead on my power supply with an alligator clip. I hooked a little sewing needle to the ground on my power supply. And then I began to search for light-emitting zones. I built my own sort of cat's whisker detector in order to keep the needle in place on a particularly bright spot I found. Now I can sit back and enjoy the warm glow of a homemade LED anytime I choose, even though it's pretty dim, but it's still cool. As far as we know, Round's research into light-emitting crystals ended here, which is a shame because he was definitely onto something. But of course, that's not the end of the story. 15 years later, in Imperial Russia, a scientist and inventor named Oleg Vladimirovich Losev noticed that certain diodes in radios started to glow a bit when in use. Losev conducted a lot of heavy research and published his findings in several languages, but sadly, they seem to have gone unnoticed. It wasn't until 1962 that a visible light-emitting diode was made practical by Nick Holoniak, working at General Electric. He's widely known as the father of the LED. The technology that Holoniak brought to the public is remarkably similar to our crystal experiment. A thin metal wire connects one side of the circuit to a small piece of semiconductive material on the other side. The LED's two leads are cut to different lengths to show you how it should be connected. The longer one is called the anode, and that connects to positive. And the shorter is the cathode, and that goes to negative. To power an LED, you can just use a simple coin cell. This is a CR2032. Then just make sure the longer lead is on the positive side, which is wider and smoother, and the negative is on the other. If you plan to use a battery, let's say a 9-volt, you'll also need a resistor to limit the current so that we don't burn out the LED. Connect negative to the cathode, the shorter lead, and we'll put a 470 ohm resistor between the positive battery and the anode. For more useful info, check out the LED Center, and there's a lot of great history at the LED Museum. For all types of project ideas, info, and inspiration, head over to makemagazine.com.
Okay, so two parts, the FASA demo product and the USB to serial converter, which you need if you have no serial port on your PC.
Okay, that's good.
Okay, so parts supplied with the FASA demo board, okay? So we have 3 fiber optic cables, 1 serial cable, 1 USB cable used for powering the demo board, and the FASA demo board itself. It's the FASA LED analyzer plus some LEDs used for demonstrating the product. And finally, the CD with some drivers and software, and a quick start guide which contains information about installing the product on the PC. The first step is remove the fibers from their packaging. Okay. Now in this case the fibers are numbered, so they go into the analyzer in a particular sequence. Okay, so the numbering, if you can see. Okay, so the fibers are installed in a particular sequence, okay, as per the label on the back of the analyzer. Okay, so 1, 2 is in the middle and 3 on the side. Okay, unscrew the coupling. Okay, take the fiber, insert in the back of it. Now it needs to be wiggled around a little bit at times. Push it forward until it hits the sensor, and then squeeze the coupling. Okay, again for the center one. So picking up fiber 2, pushing through it, wiggling it a little bit. Now in some cases it may be difficult to get in, but okay, if it's difficult to install, remove the coupling completely. Push it back so the fiber is exposed. Install it this way. Okay, push the fiber home again and screw the coupling back on. Okay, push the fiber home and screw on the coupling. Okay, these are just lightly squeezed, not too tight, or it may damage the fiber. Move the serial cable. Okay, with the white connector. This is installed on the white connector on the FASA LED analyzer. The serial cable. If you have a serial port, then that can be installed. Otherwise, we use the adapter cable. Okay. The last cable is the USB cable. Okay. This is inserted in the analyzer. Okay, and plugged into the USB port. Okay. Now, so we should have some LEDs, and the green light on the FASA LED analyzer should be turned on. Since we don't have a serial port on the PC, we use the adapter cable. We supplied 3 optical heads to be installed in any of the LEDs that you choose. Okay, so push it through. So you just pick red, green, and blue. Okay, so take the fibers. Again, loosen the coupling. The analyzer is ready to work now, except to install the software. So to start, click on Connect. The LED analyzer detects that it's connected to port 10, so that's serial COM port 10. Okay, now taking fiber 1, it's connected to a red LED. So to make some measurements, just click on Start Test. Now. Okay. So in this case we're getting an overrange condition. Okay, so to overcome this we can pick manual capture, and select the range as Ultra. Start to test. Now, this is telling us that the red, green and blue content is 100% red, 0 blue, and 0 green and 0 blue, with an intensity of 2.37% full scale, or a value of 2368. So to select the range, we can go to one range less, which is super, and make the measurement again. In this case, we're getting the same RGB content, but the intensity is measuring much higher. So this is a more suitable range for the LED that we are measuring. Okay. Now, if we take the optical head and move it to green, once again. Now, for green LED, we're getting a small percentage red, majority green, 90% green, and a small percentage of blue. Okay. This equates to a hue value of 123. Saturation value of 98% and intensity 2700. Now again, this intensity is a little bit low, so a more appropriate range for this would be the high intensity range. So I'll repeat the test. So again, we're getting an intensity of 39,200, which is a more appropriate range for the LED that's being tested. Again, the hue value of 124, so this equates to the color wheel. So the position of the colour wheel is at 124 degrees, which equates to the hue value. A saturation of 100% means it's on the circumference of the circle. If this was a white LED, it would appear in the centre of the wheel, which would give a saturation value of 0.